Okay, this last area of study, the third area of study for Unit 1, it's called matter and how it's formed, so I'll just call it here matter. So, it's about all the particles and stuff that's around us and what we know about it and all sorts of things. So, part of the thing here is how we can actually measure and find information. So, first part of it is when we measure stellar information. Alright, so we got ideas of how far stars are from us and what they're made of, things like that, and how do we know that? And we did a little bit of that in our first area of study when we looked at Wiens and Stefan Boltzmann. So they were ways we can get. Now, so let's talk about distance. So part of this distance. How do we know? Right, so how do we know how far something is? Well, there's a thing that we call parallax. And on the top of my notes, so if you hold your finger out in front of you, you close one eye, then open that and close the other. What you should notice is that in relation to the background, that your finger moves. And so, we've got this diagram here of parallax. So if we're looking at some star, so here's some star there, we're looking at that star there. Now, if we observe that from the Earth in January, because as we know the Earth goes around the Sun, so if we observe it in January, we look, along there in this direction. And so we see these stars in behind it. 6 months later, when it's at the other side, part of its orbit, the other side of the Sun, over here, we're looking at the star in that direction, and so we see these stars. So, from our perspective, what's happened is that the stars actually moved. Seems a bit strange, but one time it looks like the star's here in front of those, and then over here it looks like it's there. So it kind of, in a sense, looks like it's moved. So the simplest way that we can measure distance to a star is by using parallax. Alright, so what is parallax? Parallax is the apparent shifting of the star. So there's a couple of distances shifting in those first two. Alright, so what have we got? So if we create ourselves a nice little triangle, and let's going to draw this in red. So if I've got a nice little triangle here like this, like so, and it's a right angle triangle, and so here we're using the distance. Down here, see 1 AU, so 1 astronomical unit it's called, and 1 astronomical unit is the distance between the Earth and the Sun. Alright, because there's such a long distance, astronomical units is kind of handy. So in that red triangle, because we've got here's our angle, we've got the opposite and the adjacent, so that means that tan of P equals opposite 1 astronomical unit over the distance. So if we then rearrange, because we want to know how far away the star is from the Sun or from us, the Sun in particular, we rearrange that times both sides by d and divide by tan P. You get that the distance is 1 on tan P. Now, the thing is, these angles are very, very small. So then for small angles, as it says in your notes there, so those go in one gap under there, underneath that diagram. So for small angles, and these are very small angles, tan p is approximately equal to p. So if that's the case, then the distance is 1 over p, that parallax angle. Alright, so our distance, d, equals 1 over p. So that's the distance to the star. And that's our parallax angle. Now the thing is, the parallel, what do we measure these things in? Well, the parallax angle is measured in what we call arc seconds. What is an arc second? Well, it says in your notes that 1 arc second is degrees, minutes, seconds, so it's 1 second. What is it? 1 arc second is in fact 1 over 3,600 degrees. Alright, so extremely small angle. Now, this distance then that we've got is measured in what we call parsec, which is PC, parsec. Alright, and so over the page on the second bit there, it talks about converting degrees to arc second. So if we want to go degree to arc sec, we times by 3,600. All right, and so as also it says in there, and I already kind of mentioned this, that distances are huge. So example it's given in your notes, there's the Andromeda galaxy, which is 2.4 by 10 to the 22 meters away, which is a long, long way. So we use other units instead, and there's a whole list of the other units in your notes. So very far away. So we use other units. Alright, and these other units then end up being, more convenient for us. We can talk about astronomical units or light years, the distance light travels in 1 year, or parsec. Alright, so those sorts of things, talking about distances in those terms is much easier than, in that kind of terms. Alright, so then there's an example in your books, in your notes, so let's have a look at the example. Alright, so there's the example. Estimate the distance d to a star if the parallax angle is 0.00006 degrees. Give your answer in parsecs, light years, and astronomical units. So, as we know, the distance is 1 over the parallax angle. Now, that parallax angle's got to be in arc second. So, previously, back here, there we are. Degree to arc sec times 3,600. So, we got 0.00006 times 3,600 equals, when we do that, 0.216 arc sec. Alright, so our distance then is 1 over that. And then when we do that on your calculator, you get 4.629. Now remember that distance then is measured in parsec. Alright, because that's what that formula there is. P is in arcsec and the distance is parsec. Alright, so that's the first bit, light years. Now if you go up above your example, it gives you conversion, that bottom one. It says convert parsec to light years multiplied by 3.2616. So the distance would also be 4.629 times 3.2616. And these conversions would be things that you would put in your notes that you bring into your tests with you. Alright, and when we multiply that, you get 13.924 light years. Then the other one, it says astronomical units, and just above that says to convert to astronomical units, you multiply by 206265, and when you do that, you get a much bigger number, 954,800 astronomical units. So, as you can see from those numbers, you know, astronomers talking in terms of parsec and light years. When they talk about that, the numbers are far more manageable than astronomical units or whatever. All right, so there is a limit, of course, to how good parallax is, because as you can see, these angles are extremely small, so being able to do them, measure them, is quite difficult. All right, so up to about 100 light years, it says in your notes. Then we've got to use other things. All right, so the next bit in your notes is what's called spectroscopy. So what is spectroscopy? Basically, it's looking at the light and seeing the colours. And as we already noticed about with Wien, that the wavelength of the peak and the temperature of something was related. So we saw that earlier on in the year when we did the thermal stuff. So, but what else we can also do is, you know, from our basic understanding, we've got electrons spinning around the outside of, so we've got our nucleus in here, and we've got our electrons scooting around, and there's different levels, and so these electrons could go up and down from electrons. So if we somehow excite it up, it could drop back down, and when it drops back down, it gives off some light. And so what we can do is we can have a look and see what's going on. So in your notes there, this is kind of a bit wordy, that first bit. Now, there's also some videos, so you should look at those videos. The videos on the emission and absorption spectra, that'll explain a bit better. All right, so, and again, look at the notes to find on the website to find out what goes in your, in those gaps. All right, so as it turns out, each element has like a fingerprint, if you like. So if you're looking up at hydrogen at the top there, so this is a hydrogen gas. So if we put electricity in that and get electrons to jump around, you'll notice that there's 4 distinct bands of light that are given off when those electrons fall down. You look at the iron and you can see like there's a whole heap in iron, and then the bottom one there, sodium, and look, there's a couple of distinct, very distinct bands of yellow right there. So what we can do is we can point that up to stars, and point it up to stars and have a look and see what lines, and if we look at the star and we look at the lines and we see that there's, you know, these lines that correspond to hydrogen, then we know that there's hydrogen in that star, right? And we can do these spectral lines things, spectroscopy. We can do that on just with hydrogen gas and with iron gas and sodium gas on Earth. All right. So when we look at that, there's something very interesting to see. So again, get the notes. So this moves on to when astronomers pointed up at the sky, they saw these lines, but what they saw was that they weren't quite in the right spot. And so there's a thing called the Doppler Effect. So the Doppler Effect, and there's 3 videos on there, they're all good, particularly that car horn one, you can really hear what happens. So what happens is when something is moving, the sound or light changes to the observer. And that's called Doppler. And Doppler effect is used in medicine as well when looking at blood flow. That's just a bit of a side. So what is the Doppler effect? It's a shift in the frequency. Right, so it's and again, it's pretty wordy, so look at the notes on the website. So it's a shift in the frequency. So, for example, if we have as our observer, maybe you standing there, and here's our source in the middle, and that source is sending out waves, and as you can see, they're all circular there, and they're nice and uniform, and they're all kind of minding their own business. But if you then start moving in, or it's easier if you talk about the source. So if the source, instead of being stationary, starts to move towards you, then this is the diagram. All right, so this outer ring, so this one here, the centre of it's there, so that source would have sent out a little wave there, but then the source, because the source is moving, then it sends out another one here. Of course, that one's got bigger, and so on and so on and so on. So what it then looks like is this. So by the time the source is there, it's about to send out another wave there now, right at that point. And so what we've got is we've got these waves squeezed together here, and on the tail end we've got them moving apart. And so we've got shorter wavelengths here, and we've got longer ones there. And so what that happens is that it shifts those spectral lines one way or the other. So in shorter ones, it shifts towards the blue end, and the long one, it shifts towards the red end. So if we have a look at a diagram that kind of illustrates. Alright, so in the middle diagram here, the green one, that's if everyone's standing still, if the source is still and you're still. But the one at the top is if it's moving towards you, all those little, so it's this one, the wavelength shortens and it goes towards the blue. So it appears to us to look like this rather than the middle one. And of course, if the source is moving away from you, so here's our sources, so if that's moving away, that then stretched out that wavelength, made it towards the red, and so that appears more ready to us. Alright, so why is that significant? Well, what it's significant is the redshift bit. And the significance of the redshift, and there's a video, redshift and Doppler's effect, is that if galaxies are moving away, then the wavelength would be increased. So this is diagram here kind of illustrates. Alright, so here's our stationary star at the top, sends its wave, and here's us stationary. But if we have a star that's moving away, what that does is it stretches out that wavelength, as it says there. And so to us, the moving star, one moving away, looks more red than the one that's stationary. Alright, so but how do we know that? Well, how we know that is this. So if we point and we look at a spectroscope, a spectral line analysis of something on Earth that's stationary, so we might look at a particular spectral pattern, spectral line pattern, and we might get the one, you know, that's at the top here, for example. So there's this one up here. All right, so this one A, that's what normally we would see, and then when we pointed it up to the and looked at the star, we see this one. Now, what we notice is there's some similarities. So look, there's these double lines here and here. Then there's this single line here and here. And then there's that gap, and then there's this next one. So the pattern looks the same. So that suggests to us that these two, this one here and this one here, are produced by the same element, the same gas. But on the frequency aspect, instead of those double lines being there, they're there, they've moved. And in particular, what we noticed is that they've moved towards the red. Alright, so there's red shift. So we observe red shift. Now, we know red shift is associated with something that's moving away, and so what that means is that the galaxy is moving away. So galaxies therefore moving away from us. So the red shift of the spectral lines then can do the velocity, because the amount of this shift, so how far these things have shifted, whether it's that much or this much or further, depends on the speed that it's moving. So in particular in your notes it's bolded too, so if you have a 10% increase in the frequency, or sorry, not the frequency, the wavelengths, in the wavelengths of spectral lines, what that leads to is a 10% of the speed of light away from the from the observer, and so that's in your, and so this bit here is quite critical. So therefore we know how fast things are moving away from us if we care to measure that. Now, somebody did care to measure that, And the person who did care was Edwin Hubble, and we've come up with, or he came up with, Hubble's law. And NASA liked that so much that they named their space telescope over it. So Edwin Hubble, what he did, oops, wrong one, I need a diagram. So what he did was he decided, all right, what I'm going to do is I'm going to draw a graph. I'm going to draw a graph of the distance in megaparsecs, just so that it makes the numbers nice and easy, and the recession velocity. So we know all these are moving away from us, because we know that because of the red shift of their spectral lines. So we know that. And so what he did is he decided that that's what he was going to do. And kilometres per second, just to make life easier, just like the megaparsecs. So all of these little dots there, the different stars, and what he noticed is that there's kind of a linear trend, and so then he put his line through there. And so what he noticed then is the further a galaxy is away from us, the faster it is moving away from us. So if that's the case, it would suggest things are expanding. Now, if you look at and you work out what that is, then the velocity is equal to some constant times the distance. And if I go over here, and so the velocity is this thing h0 times the distance. Now the velocity, because of what Hubble did, that's in kilometres per second. The distance is in megaparsec. And then there's this constant, which is the gradient, and that's called Hubble's constant. And it has a value of 70. And of course it's got units, and the units are that's just to fit in with the units of the other thing. Alright, so if we measure the redshift of something, and so like I said before, that parallax has a limit, but now if we measure the redshift of something, we'll know how fast it is going away from us, and from that we can work out the distance in megaparsec. So for things that are further away than those 100 parsecs, so megaparsecs, we can measure that quite well. Alright, let's have a look at an example. Okay, so a distant galaxy is found to have a redshift of 15%. Calculate its velocity of recession. So 15% means 15% of the speed of light. So 15% of the speed of light, 15% is the decimals 0.15, times the speed of light, which is 3 by 10 to the 8 metres per second. Multiply that out and you get 4.5 by 10 to the 7 metres per second that star is moving. Alright, deduce the value for its distance. So V equals h0 times d, the distance. Alright, now alright, so the distance, and I've just noticed in the notes that I've got there, I've made a mistake with my my calculations, because I've forgotten to change our metres per second into kilometres per second, and given that there's 1,000 kilometres in a metres in a kilometre, I should say, that I need to divide by 1,000. So that means that the velocity would be 4.5 by 10 to the 4 kilometres every second. So that's the number I need to use, not the number I've used. So I got my power of 10 incorrect. So 4.5 by 10 to the 4 is equal to Hubble's constant, which is 70, times the distance. So then the distance then, and again that my powers of 10 is out. Alright, so as I said, got my powers of 10 out. So when you divide 4.5 by 10 to the 4 by 70, you get 643 megaparsec. Alright, which is a very long way away. Alright, so we can work out that distance. Now, also mentioned about expanding Hubble and the expanding universe. So it seems like things are going further away from us. And here's if you think about it a bit like this, you know, if you've got all these dots on a balloon are our stars, and if you blow the balloon up, then the stars, like, they move apart, and they're moving apart all in relation to each other. So, and when it doesn't matter what direction the stars astronomers look at, that is the case. There's always a redshift. So that suggests that what we've got is we've got an expanding universe. So if it's all expanding, so everything's going out, then thinking is, alright, so if it's all expanding, it must have, in some point in time, come from in here somewhere, and it's all then spreading out. So it must have been at some point in time a lot smaller than what it is. Alright, what do we know? Well, from our mechanics we know that velocity is distance over time. So if we rearrange that, times by time divided by velocity, the time is the distance over the velocity. Now, Hubble's law says that velocity is Hubble's constant times the distance. So if I then put that in here, I get the time is the distance over Hubble's constant times the distance. And so the distances cancel, and it says then that the time will be 1 over Hubble's constant. And so, as it says there, 1 over Hubble's constant is an estimate of the age of the universe. Alright, now there was a couple of videos on Hubble's law and this, you should watch those as they're good. Alright, so what would the age of the universe be? So in this next example, we'll have a look at that. Alright, so here's a little bit of a calculation for us to figure that out. Okay, so the time is 1 on Hubble's constant, which is 1 on 70, and that's megaparsec kilometres per kilometre seconds. So megaparsec to kilometres, so 1 megaparsec, 1 parsec I should say, is 3.0, again looking this up in the thing, by 10 to the 16 metres, that's earlier on. So that's metres. So to kilometres we've got to divide by 1,000, so that's 3.086 by 10 to the positive 13 kilometres, so that's all good. And megaparsec, Well, mega is 10 to the 6, so times that by 10 to the 6, and so that's 3.086 by 10 to the 19 kilometres. Alright, so the time then will be, oops, let's go back on that. The time will be 1 over 70 times by 3.086 by 10 to the 19. And when you do that, you get 4.4 by 10 to the 17 seconds. Alright, and then if you change that into years, alright, work out how many seconds there are in a year, and then divide that into that, you get 1.4 by 10 to the 10. Now, 1.4 by 10 to the 10 is 14 by 10 to the 9. 10 to the 9 is a billion, and so 14 billion years is an estimate of the age of the universe. Alright, there's a fair bit in that stuff. So now, problem set number 1. Make sure you have a look at those videos. Those videos are pretty handy. They have some good animations and things like that to help you